Hey guys, so we're getting ready to start chapter 3 today, and we're going to start with something I hope is pretty much a review for you. Okay, the beginning of chapter 3 starts with systems of equations. So the basic question you see there initially is, what is a system of equations? A system of equations is two or more equations that share a solution. Now, the reason why I say two or more today, and in fact, most of the next 2 weeks, we're going to stick to two equations. And when we have two equations, we have two variables. Then once we hit second quarter, once that starts, we will actually look at systems with three equations and three variables. Those are a little bit trickier in how we solve them, but technically a system can have as many equations as you want. But as I increase the amount of equations, that also increases the amount of variables. So the next question, what is a solution to a system? A solution is for our two equation system, an ordered pair that we're going to go with works in both equations. What I mean by that is that it is an ordered pair that makes both equations a true statement. Now, when we increase to more equations, for instance, when I increase to three equation systems, it will be an ordered triple instead of an ordered pair, but we'll cross that bridge when we get there. You can solve systems a variety of methods. We are going to actually look at four methods. We are going to look at graphing, substitution, elimination, and we will look at matrices. Right now we're going to talk about graphing. Now, when we graph, one of two things will happen. Either the first scenario there, the lines will cross, and when the lines cross, we have one solution. And that solution would be right there where those two lines meet. Whatever that ordered pair is, that would be my answer. Now, sometimes I'm going to graph this system, and you're going to get that scenario in the middle where the lines don't touch at all, and in fact, they're parallel lines. When that happens, this is a case of no solution. And I hope that you're thinking about graphing and thinking about lines, and the only way that two lines can be parallel is if they have the same slope. The third scenario would be is if I look at my two equations, and this is going to happen most of the times if my equations are given to me in standard form, and then when I solve them and get them in slope-intercept form, they actually end up being the same line, meaning that they reduce to the same thing. And when I go to graph them, since they're the same line, they line up right on top of each other. And this is a case of infinite solutions. And again, that only happens when they are the same line. So in order to do this, to solve by graphing, the thing of utmost importance is that we have to make sure that the equations are in slope intercept form. That means that y is by itself. Once I've done that, all I want to do is graph them both on the same coordinate plane and see if they intersect, where that point would be. If not, if they're parallel, then there's no solution. Or if they end up being the same line, then it would be a case of infinite solutions. When it is infinite solutions, you do need to graph that line to show that answer set. So I'm going to start here. I hope this ends up being super easy for you. Like I said, you did do this in Algebra 1, so there should be some familiarity there. On Monday, we will go ahead and look on how we do this on the graphing calculator also. So on number 1, let's look at that first line here. I am really hoping that we remember when we graph a line, this is in slope-intercept form already. need the y-intercept first. Our y-intercept is -8, it's down here. Our slope is +1. Now, normally when we graph a line, we only need to move the slope one time and then we can draw it. I will tell you with these systems, we would like to move our slope as many times as possible because that will help us when we go to graph our line. So a slope of 1 either goes up 1 to the right 1. And like I said, we can do that a bunch of times. It could also go down 1 into the left 1. So there would be my line. And lucky for us, that second one is also in slope-intercept form. So go ahead, start with my y-intercept, which would be a +1. And my slope is -2. So that means either go down 2 to the right 1, or I could also go up and to the left. Now, in this case, I can already see where they cross. So when I draw this line, hopefully you can see also that the solution to these, where these guys cross, is down here at +3, -5. When we do this, I do want you to identify the solution. So don't just leave the two graphed lines and expect me to know where the solution is. I need you to write that solution out so I know that you understand what that means. As I mentioned earlier, what the solution technically means, or the way that you can check it, is if I plug this ordered pair into both equations, this actually works out. For instance, in the top equation. Not that I need you to show me this every time, but just so you understand where this is coming from. In this top equation, if I plug in the x and y, if I plug in y as -5 equals 3 minus 8, this one does check out. 3 minus 8 is -5. And in the bottom, if I plug in the ordered pair, -5 equals -2 times 3 plus 1. -2 times 3 plus 1 is -5. So that's what I mean about the ordered pair, quote, working in both equations. And not that you need to show me that work on every equation, but just so you know that it's available to you if the situation arises. Okay, go ahead at this point, try the second one. It's very similar to the first. They're already both in slope-intercept form. So pause the video, try it, and then come back and check. Okay, hopefully we match up. Both of those lines are already in slope-intercept form. That made my job pretty darn easy. Just graph them, and the majority of the time I will find one solution. These will be intersecting lines where I can identify that point of intersection. You do need to write that down. That point was -2, 4. All right, let's look at the next one. Now, as you look at these next couple, what you will notice is that not all of the equations are in slope-intercept form. All that means for us is I have some work to do. So if I run across any equation, like number 3, neither one of these are in slope-intercept form. So I have to take care of both of those things before I can graph. So if I look at that first equation, again, y is not by itself. The first thing I would probably do is add x to both sides. So I would probably have 6 plus x equals -3y. Then I'd have to go back and divide everything by -3. So this would look like -2 minus 1/3 x equals y. Once I get to a point where I'm in slope-intercept form, then I can go ahead and graph that. So this y-intercept would start at -2. If the slope is -1/3, it's down 1 to the right 3. And again, if you remember our Algebra 1 review that we did way back at the beginning of the year, we reviewed graphing lines, and I told you everything that we reviewed in that had a purpose, because I knew we were going to need it fairly quickly. And this is just another one of those examples. Okay, if I look at that second equation, again, not very close to getting it in slope-intercept form. In this case, since I already have the x and the constant on the same side, I would probably subtract the 3y to start, just because it would be less work for me. So if I did that, if I subtracted the 3y from both sides, I would then have, start the new one, I'd have x plus 18 equals negative 3y. Okay, then go ahead and divide both of those sides by negative 3 to get y by itself. So I'd end up with negative 1/3 x minus 6 equals y. So this y-intercept is at negative 6. This slope is down 1 to the right 3. Now, hopefully, you've noticed at this point that these lines are parallel. And maybe you even noticed that from the very beginning. These lines are parallel because they have the same slope. When this is the case, this graph technically has no solution. Now, on a no solution graph, I do need you to identify that this has no solution, meaning I need you to write that out. I also do need to see the two lines graphed because that's what visually shows me that there is no intersection here. These lines will not cross. Okay? Similar to before, go ahead and pause the video. Try number 4. In number 4, one of them is done for you, meaning one of them is in slope-intercept form, and one of them is not. Again, hopefully we agree. When I got that first equation in slope-intercept form, and I graphed it, and then I want to look at that second equation, it was the exact same line. So this is one of those scenarios where if I were to graph that other equation, it would lay perfectly on top of the other line. This is a case of infinite solutions. Again, when it's infinite, I need you to identify that by writing it there for me, and I do need to see that one line graph because every point on that line is an answer to this equation. Okay, similar with number 5. In a second, I'm going to ask you to pause it. Make sure you remember that second equation, something that looks like y equals negative 7. That's just a horizontal line. So pause it, try it, then we'll check. How'd we do? Again, when I got that first line in slope-intercept form, I ended up getting y equals negative 1/3 x minus 5. Graphed it, graphed that other horizontal line, and my intersection point was 6, negative 7. Please don't forget to identify that intersection point if you have one. Don't just make me guess that you understand that where the lines cross is actually the solution. All right, looking at number 6. Again, take a moment, pause the video, try them both, and then we'll check it. Okay, once again, hopefully we agree. Now, granted, this one was a little bit messy because the y-intercept was not perfect. It was negative 1.5 or 3/2, depending on how you left it. But because these end up being the same line, it wasn't really that big of a deal. Okay, last one. Everyone's favorite, word problems. So we can look at the scenario, but at the end of the day, we need to create two equations to fill the requirements of making a system for this. So my two different scenarios are my two different stands I'm dealing with. So I'm going to look at the first one that says one stand charges $1.50 per ounce in a free bag. So that equation would look like y equals 1.5x. Or, because I like things better in fraction form when I'm graphing, I could call this y equals 1.5 as a fraction is 3/2. Now my second situation says a second stand charges $6 for a jar that you can fill for 75 cents per ounce. So again, I can either think of y equals 6 plus 0.75x, or if I make it in fractions, I can say y equals 6 plus 0.75 is 3/4. So what I want to look at in graphing these, I want to graph this equation and this equation as my system. So again, let's go ahead, take a second, pause this, graph them, see how we end up. Okay, so hopefully we agree on the graph, and the solution is 812. But to answer these two questions, you have to have some understanding of what the graph means. The x's on our graph were the ounces, and the y's on our graph were the price. So if our solution is 812, that means how many ounces must be bought for the cost? That means 8 ounces